Hey everyone, this is lesson 822 on areas of regular polygons. Prior to this lesson, we've been talking about polygons and angle relationships within those polygons. So here's a little bit of a review of a couple things. We talked about calculating interior angles, sum of interior angles. That was the first thing we talked about in the last lesson. We came up with this formula that we could use to calculate that. So as long as we know the number of sides, so a lot of times it's represented by the letter N. If we know there are N sides, then we could determine what the sum of the interior angles. So all the interior angles added up together. If we just want to know what one of them is, so each interior angle, then really we could just take that same formula and divide it by n, right? Which is where this second formula comes from. So if you know how to find one interior angle using this formula, then you should know how to find all of them because they have the same, you'll notice the top is the same. We also talked about exterior angles as well, and one nice part about the sum of the exterior angles is they always add up to 360 degrees. So there's really no formula, no numbers to plug in there. The answer will always be 360 for sum of the exterior. But when we want to know what one of them is, each interior angle, we could take that 360 and divide it by the number of sides. So in this case, 360 divided by n. All right, so these are the four main things that you needed to know. There was also the connection between interior and exterior. They are supplementary. They should add up to 180 degrees. So if you could figure out the interior, you could subtract that from 180 and it'll give you the exterior. Or if you know the exterior and you subtract it from 180, it should also give you the interior. So there's another way to get interior and exterior angle. But these formulas work with knowing the number of sides. All right, so if you don't already have that in your notes, I think the last lesson, even though I gave you all those formulas, I didn't necessarily summarize it at the end. So this would be a good time to kind of just copy that down. And then another thing I wanted to review, which was actually even before our polygons, was some right triangle tools, which we're actually going to be using some of these today in our lesson. So that's one reason why I wanted to add this to things to review. So Pythagorean theorem, make sure you understand what that is. Our trig, sine, cosine, tangent. And then our special right triangles, we have both 30, 60, 90, and we had a 45, 45, 90. All right, so those are the relationships you needed to know with those triangles. So this is a good summary of key information. So for sure, this would be something worth having in your notes, nice and organized. So in case you need to look it up somewhere, this would be a good page to turn to. In case you didn't have it somewhere else. All right, and what we're trying to learn today is how to find the area of regular polygons. Even though it's important to know how to find the area of all polygons, we're going to focus on regular polygons. It's a bit easier, and there's a process to it that would probably make it a lot easier for us. All right, so there is no formula for, or no easy formula for finding the area of a polygon, which we don't necessarily know how many sides. So if you do remember, we have formulas for triangle, for rectangle, and so if we could just use some of those formulas, then it'd be a lot easier for us. And so there's a couple strategies to find the area of a shape like this, and this is a regular hexagon. And I'm going to go over one strategy that we could apply to all polygons, all regular polygons, which should make things a little bit easier. All right, so key information here, if you didn't already notice it, is I've given us the formula for the area of a triangle. Right, so that's something we're going to need to know. Now, I could also use the formula for area of a rectangle, which is just base times height. But then I would have to think about how can I turn this shape into rectangles, which is a bit more challenging. So turning this shape into triangles is actually something that we could do a lot simpler. All right, so here's our strategy for calculating the area of this shape. Let's turn it into triangles. And so one approach, I'm going to zoom into this, is, here, I'll do it like this first. So if I actually draw in all my diagonals, all right, so all my diagonals that intersect at the center, you'll notice now I have a total of, what is this, 1, 2, 3, 4, 5, 6 triangles that are all congruent. They're all the same triangle. So instead of us trying to find the area of this hexagon, really all we need to do is find the area of one triangle. All right, if I could find the area of one triangle and then multiply it by 6, then that should be the same area. All right, so now what we've just done is we've taken this hexagon problem and turned it into a triangle problem. All right, so let's get started on that approach. So I'm going to add in some specific lines here. So from the center, since I'm just really focused on one triangle, all right, let me do this. All right, so I'm going to, let's take this triangle. All right, so I have this triangle here, and I'm going to just zoom in. So we're going to zoom. And I know this measurement is 8. So I'm going to have, what I do know is I'm going to have a total of 6 triangles like this. Right? If you remember, if I actually draw these in, there's actually a total of 6 triangles in this picture. So I could already start a formula for this, and that's going to be, let's see, the area of our hexagon. I'm going to put area of our hexagon is going to equal to 6, right? We're going to have 6 triangles times the area of the triangle, which we already know is going to be 1/2 base times height. All right, so here's our formula that we're going to be using for our hexagon. All I need to figure out is what's my base and what's my height. Right, so here's my base and here's my height. So I need to, if I'm looking at my triangle, I have a base and a height of that triangle. Well, it looks like I have one of those numbers, right? So let me, right, so I have 8. So I'm going to put that into my formula. The only thing I'm missing, so far we haven't really calculated anything. All I need to do is know my height, and I pretty much have everything I need. So this is where the work comes in. So if I'm going to draw in my height here. So if I actually draw in the height of this triangle, this actually splits it into 2 right triangles. And so now I could use anything I can, or any tools I have regarding right triangles. So that's kind of why I mentioned them earlier. So I have Pythagorean theorem, I have trig ratios, I have special right triangles. All right, so by splitting it up, what I do know now is that half of it is 4. Right? Half of it is 4. 4 and 4. Okay. And so how can I use that information? Well, if I want to figure out what the height is, I'm going to need either some angle information or another side, maybe the hypotenuse. So I don't have the hypotenuse, so I can't use Pythagorean theorem, but perhaps I could figure out some angles information, right? And so this is what we're going to use. This is where we're going to use some angle knowledge that we have. So if you don't remember, a full circle, if you go around in a full circle, is going to be 360 degrees, right? 360 degrees is a full circle. So if you notice, kind of like almost looks like a pizza, right? If I go around in a circle like a pizza, and I've cut it into 6 slices, then what's the measurement of one of these angles, right? So this is what we're going to do. We're going to take, if I want to know the measurement of one angle, which we call the central angle, I'm going to take 360 degrees, which was the total, and I'm going to divide it by the number of angles I have. It was 1, 2, 3, 4, 5, 6, right? 6 sides, 6 angles, 6 slices of pizza, however you want to think of it. And so I'm going to take 360 divided by 6, and that gives us 60 degrees. So that means these angles here are 60 degrees. 60 degrees. How does that help us? Well, if we look at our triangle that we just drawn out here, if this angle here is 60 degrees, then what happens if I cut it in half? Right? So now we've had, this is what we call an angle bisector, which means our angles here are going to be 30 degrees. So that's 30, that's 30. Now, if you haven't seen it already, that pretty much means we have created a 30, 60, 90 triangle. So now we could use our special right triangle tool to solve for our height. Okay, so if this is 30 and the short leg is 4, then what does the long leg equal to? All right, so if you don't remember, definitely look back at the tools that we went over. So if I know the short leg is 4, what does the long leg equal to? So let me go back up here. If the short leg is 4, then what does the long leg equal to? All right, so x and x root 3, so this must mean this is 4 and 4 root 3. All right, so let's apply that to this problem. So now I know this is going to be 4 root 3. So now I know the height is 4 root 3. We're going to take that information and we're going to plug it in, 4 root 3. And now we have everything we need to. So that was really the hardest part, is making sure we knew our special right triangles. So now we could simplify this. I would probably multiply everything that is in the square root, or you could do it in steps. Actually, I might do, since I know 6 is going to be last, I'll do everything in the brackets first. So 1/2 of 8 is 4, and 4 times 4 is 16. So one triangle has an area of 16 times the square root of 3. That's one triangle. But we have 6 triangles, so the area is going to be equal to, I believe this is 96 times the square root of 3. Right? And these are going to be square units. All right, so there's the area of, oops, let's use a different color. There's our area of the hexagon. If you put that into a calculator, you'll get, this is approximately equal to 166.3 units squared. All right, so that's pretty much what we're looking to do. I should be able to give you any regular polygon, and you should be able to do similar steps. Now, on this one, we happen to be using our special right triangles. It's very possible that this is not a 30-degree angle. It's not always going to be 30-degree. So we're going to always have to figure out what the central angle is. And then we're going to go from there. All right, so coming up I have 3 other polygons. They're all different. And we're going to see how the work changes for each one. But you'll notice most of it, this was very short for the most part. The hard part was just making sure we knew the base and the height. So if you have at least one of those, then hopefully we can find the other one. All right, so let's calculate the area of this shape. So hopefully you took good notes on that example, because you're going to have to do the same thing with this one. All right, so I'm going to get you started, and then I'll see if you could finish it on your own. But okay, so our goal is to calculate the area of this hexagon. It's also a hexagon. So we have 1, 2, 3, 4, 5, 6 sides. All right, so as soon as you know how many sides there are, that already tells me what I usually like to do at that point is just start to create our formula. So since we're always going to be focused on triangles, the formula is 1/2 base times height. All right, so this, we pretty much have it set up. All I have to do is figure out the base and height of this triangle. All right, so what's the triangle I'm looking at? Well, let's draw it in. So from the center to the vertex, right? Now there's a total of 6 triangles. We don't have to draw in all of them, but if you want to draw in all of them, you can. I just like to draw one in just so I could focus on one at a time, since we don't really need to see the rest of them. But what we do need to know is what is the central angle, right? So we talked about that before. So if I want to figure out the central angle, we're going to have to remember what all the angles should add up to. All right, so if I add up all the angles in the center, what should they add up to? All right, let's see if you got that correct. So it should add up to 360 degrees. So I'm going to take 360 and I'm going to divide it by 6, right? Because there's going to be a total of 6 triangles because there's 6 sides, right? And this tells us that this is going to be 60 degrees. All right, so this should be just like the previous problem we did. Okay, so that means our method should be very similar. Okay, so we know the height. Let me highlight this. So we know the height of this triangle is 4. Oops, I'm sorry, the base of this triangle is 4. What we don't know is the height. So let's figure out what the height is. Let's see if you remember this. So the reason why we needed to know the central angle is so that we could confirm that this was a 30, 60, 90 triangle. And if the base measurement is 4, then that means half of it is 2. So then what does the height equal to? All right, let's see if you could tell me what that is. All right, if you said 2 times the square root of 3, you would be correct. All right, so this is 2 times the square root of 3. That's just us knowing our special right triangles. No calculations needed there. No trig. It's not a guessing game. It's the same pattern every single time. All right, so definitely review that if you need help with that. All right, so I'm going to plug in 2 times the square root of 3, and then that's it. Now we just have to simplify it. So the area is going to be 6 times, and so I like to do all these at the same time. So half of 4 is 2, and then 2 times 2 is 4. We're left with 4 times the square root of 3. All right, so one triangle. That's another possible question. I might actually just ask you, what is the area of one triangle? Instead of asking you the area of the whole hexagon. So that's why it's kind of good to separate these two answers. And so this would be 6 times 4 is 24 times the square root of 3. And these would be units squared. All right, which I believe that comes out to approximately 41.6 units squared. All right, so there's an exact answer for us, which I actually prefer that answer. But if a problem asks you for an approximated, then you would have to give a decimal answer, which means you're just typing that into the calculator. All right, so hopefully you saw similarities between this problem and the one before it. The work is almost the same. You'll notice I really just have 2 lines of work, 2 lines of work, and then the answer. So it's really not a lot. The hard part was happening on the picture. So this, just by looking at the picture, it tells me what you know or don't know. So when we have a test on this and you're turning in your work, this is what I'm going to be looking for. I'm going to be looking for some demonstration of where these numbers are coming from, right? If I don't have any picture and magically you give me these numbers, I would question where you got that information from. But if I could see it on a picture, then that tells me a lot, right? All right. All right, so let's try this next one. So this one is not a regular hexagon. All right, so let's see if you could tell me the name of this shape. Right, what's the name of the shape? It is a regular what? All right, if you said, I don't know, then I'm going to tell you how to figure this out. First, you start by counting the number of sides. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this has 10 sides. So since n equals to 10, I know this is a decagon, right? Or it's a regular decagon. All right, so if you didn't know and you said a pentagon, then that would have been technically correct as well. But decagon would have been the preferred name. All right, so why is that important to know? Well, when we're trying to find the area, just like the hexagon, we had to find the area of one triangle and then multiply it by 6. But here, how many triangles is there going to be if we actually draw in all the triangles? So from each vertice to the center, right, kind of like a pizza, if we cut it up into it's going to be how many slices, right? So how many slices of this decagon is there going to be? Well, 10 sides means we're going to have 10 slices, 10 triangles. So that means we're going to do 10 times the area of one triangle. So the triangle formula doesn't change. 1/2 base times height. That doesn't change. The only thing that's changed here is this number on the outside. Okay, so if we're going to focus on the triangle, so if I'm going to draw in a triangle. All right, so if I have my triangle there, that's the one I'm focused on. You'll notice it looks a little bit more narrow than the previous one. So that tells you something. This angle in the middle has changed size. So it's no longer 60 degrees. So the question is, what is the central angle? What is the central angle? All right, let's see if you could tell me what you think that angle is going to be. All right, so if you remember, all the angles in the center should add up to 360 degrees, but the central angle here is going to be 360 divided by, last time we divided by 6 because it was a hexagon. This time we're dividing it by 10 because it's a decagon. All right, which means we're going to be left with, this is 360 divided by 10 equals 36 degrees. All right, so how does that help us? Okay, well, that means since this angle is 36 degrees, what is the measurement of just half of it? Let me zoom into this. So that means this little piece here is going to be, see if we can squeeze that in. Okay, that's going to be 18 degrees. All right, so half of 36 is going to be 18 degrees. All right, so this is getting very narrow. So what I'm going to do is I'm going to redraw this triangle. Let me move this stuff up here. All right, so I'm going to redraw this triangle so that we have more space. Let me see if I can squeeze it in over here. All right, so what I need to figure out are the base and the height. So it looks like, if you didn't notice, this one, they've actually given us the height already. So the height is actually 5. So what we do want to figure out, though, is since I know this measurement is 18, and I know the height is 5, I'm going to put 5 in this height spot, right? So since that's given to us. All right, so now I need to figure out the base. Right, so how do we figure out the bottom part here? Well, if I focus only on half of it, right, if I really only just want this piece, then if I have an angle and I have a side and I'm trying to figure out maybe this piece, then I can use one of my special right triangles. This is not a 30, 60, 90. This is not a 45, 45, 90. We cannot use Pythagorean theorem. Our only option is to use either sine, cosine, or tangent. Okay, so what are we going to use? All right, so if this is 18 and we're looking for this missing piece over here, which is the opposite, And we already have 5, which is the adjacent. Which trig ratio are we using? All right, if you said tangent, then you'd be correct. All right, so let's set that up. So tangent of 18 degrees is going to be equal to, in this case, it's going to be x over 5. And so when we solve for x, we're going to end up with 5 times tangent of 18. All right, so what do I do with that information? Well, we don't need to know just x, but we want to know the whole base. Right? So that means there's actually 2 x's here. So the base is actually 2 times 5 tangent 18, which is 10 times tangent of 18. All right, that's what we're going to put up in this formula. 10 times tangent of 18. All right, so this is where most of the work happens. This really just turned into a trig problem. This part here with the area is really not the hard part. It's coming up with this use of tangent. That's really where the more challenging part is. Now, once we have everything filled in, we could simplify this. So we're going to have area is equal to 10. I'll leave that till the end. And I have numbers here. I have 1/2 of 10, which is 5. And then 5 times 5 is 25. So I'm going to have 25 times tangent of 18. So that's what one triangle equals to. And so the whole hexagon is going to be 250 times tangent of 18. This is going to be units squared. All right, so there's our area. Now, if we put that into a calculator, it's going to give us a decimal answer. I believe this one is 81.2 units squared. Let me just double check that real quick. 250 times tangent of 18. Yeah, 81.2. All right, so there is, let me separate this just a little bit. All right, so hopefully you see the connection between these. With a 30, 60, 90 is a little bit easier since we have shortcuts for special right triangles. If we don't have a special right triangle, we still have the tools that we need. We still have them available to us. So trig always works as long as you have an angle and a side. So that was perfectly fine. All right, and then let's do, we're going to do one more. And this is a regular pentagon. All right, so here's a regular pentagon. So let's see if we could do this one. I'll try to do this one a little bit faster with you. So our first step is to figure out how many sides. So in this case, n equals 2. You tell me. All right, n equals to 5. All right, very good if you got that correct. There's a total of 5 sides, which tells me right away, this tells me, okay, I'm going to have area equals to 5 times 1/2 base times height, right? This is always the same, 1/2 times two numbers, base and height. And the base and height are of the triangle from the center, right, to the vertices. And so we have these triangles in here. We need to figure out the central angle so that we know what that angle measurement is. If it's a nice angle, then we could use our shortcut. If it's not, then we're going to have to use trig. So our central angle here, we're going to take 360 degrees divided by 5. And so what is 360 degrees divided by 5? Well, that's going to give us 72 degrees. Well, 72 is the whole angle, but if we cut it in half, then that means we're going to be left with 36. All right, that is not a 30, 60, 90 triangle. That we're going to have to use our trig. In this case, we already have the base given to us, so I'm going to put that into our equation already. All right, so let's highlight that. So that's that. All we need to figure out is our height. Okay, so that means we're going to, I need to know what half of 15 is, which is going to be 7.5. And we're trying to figure out what our height is. All right, so we're going to use trig. This is going to be opposite of 36 is 7.5, and we're looking for the adjacent. So again, we're going to use our tangent ratio. Okay, so let's do that. So tangent of 36 is equal to 7.5 over h. All right, so in this case, the h is on the bottom, so try not to mix that up. Adjacent goes on the bottom, which means when we solve this, right, I'm going to skip some steps here, but when we solve this, you're going to end up with h equals to 7.5 over tangent of 36. All right, if you need help solving that, trig problems like that, then review your notes on your trig ratios. All right, so we figured out the height. That's all we needed to know. We don't need to multiply it by 2 or anything. The height is the height. And so we're going to put that into the formula. 7.5 divided by tangent of 36. All right. So just by writing that out, the way I've written it out, even if you make mistakes after, if I could see that in your work, that would tell me you pretty much know what you're doing. If you can't simplify it from there, then it's just calculation errors. It doesn't tell me, if you mess up from here on, it doesn't mean you don't understand what you're doing. It just means you've made calculation errors. So this tells me a lot. Just by getting this is huge information for me. Now, let's simplify this. We're going to do, I always like to leave the sides 5 on the outside. So now we're looking at multiplying 1/2 of 15, which is 7.5, and we're going to multiply that by 7.5. So what is 7.5 times 7.5? Right? This is going to be, this is going to be 56.25 divided by tangent of 36. All right, so we have a fraction here. Let's make that bigger. All right, so one triangle is going to be 56.25 divided by tangent of 36. We have 5 of them, so this is going to be, if I take that and multiply that by 5, then our area is 281.25. Oops, let me move this stuff over. It's in the way. This is going to be over tangent of 36 units squared. All right, so this would be an example of an exact answer that has a fraction in it, and then approximated, I believe the answer, I think this comes out to, let me just do it, tangent of, what were we saying, 36? Yeah, 387.1 units squared. All right. So this is what you need to be able to do. I know this kind of took a while, but every problem like this, it could be a little bit different, but the steps you'll notice are kind of the same. I needed you to see a lot of problems like this, and if we were in class, we probably would have done even a couple more. So we have a pentagon, 5 sides. We did a decagon with 10 sides, and we did hexagon with 6 sides, and we actually did 2 of those. All right, so hopefully if you at least know how to do a hexagon, that would probably be the best one at the very minimum to know how to do. All right, so that's it for now. Hopefully you learned something here, and we'll see you next time.